Alright, now it's time for Dr. White's Fun with Graphs. And today we are going to specifically talk about and review bipartite graphs. So what is a bipartite graph? Well, the definition of a bipartite graph is that it's any graph where you can find some subset of vertices such that every edge has exactly one endpoint in that set and one endpoint outside of that set. So the examples would be something that looks like this. This is my set A, and this is my set A complement. As you can tell, every edge has one endpoint in A and one endpoint in the complement. And so that's the definition of a bipartite graph. It's bipartite if you can split the vertex set into two groups such that the enemies all lie on opposing sides. As a counterexample, this graph, at least the way I've drawn it, does not look like a bipartite graph, because if I were to choose these three vertices to be my set A, and then that makes these three vertices my complement, and I see the problem is that here's two vertices, here's an edge that connects two vertices in the same part of the partition, the same component, and that's forbidden for a bipartite graph. Does that mean that this graph is not bipartite? Well, no. In order to actually verify it's not bipartite, you actually have to verify it for any choices subset. This is an existential quantifier. Of course, it turns out this one is not bipartite because you can see that there's a 5 cycle, but that's a theorem we'll cover later. So this one is not bipartite. So as an example of a real-world graph, here's the graph of all the U.S. representatives in the year 1961. The vertices are colored based on which political party they're in, and there's edges between two vertices if those two politicians voted the same way on a given bill. And of course, that's not actually a bipartite graph, but you sort of get this bipartition in that if you group and you weight the edges based on how often they voted together, you start to see that there is this partition where the blue vertices tend to vote together and the red vertices tend to vote together. So it starts to look like a bipartite graph. So in the real world, when you look at network data, you can try to see how close your graph is to being bipartite, and sometimes given a data set, you'll actually see an actual bipartition. And in this case, the bipartition actually agrees with political alliance. The fact that you see edges going across is actually a good sign in this case, because it's saying that in 1961, people actually voted across the aisle, whereas these days they don't. But anyhow, this is a good example of a graph and an application of why you would study bipartite in the real world. In fact, oftentimes in applications in the real world, they look at data because they don't know what the partitions look like, and they're trying to see in big data research if they can group customers together, because if you can figure out how to group customers together on what they like, then you can sort of figure out what advertisements to send them. Now back to our course. The main homework question, of course, is how do you determine if a graph is bipartite? I mean, if I draw the bipartition, it's obvious, but for instance, in this graph on the left, it's not clear. I mean, clearly I can't group these two together because there's an edge. So maybe I group these two together, and, the goal is, can you find a set of vertices that works? And likewise, is this graph bipartite? And so the theorem that we covered in class is that a graph is bipartite if and only if it does not contain an odd cycle. And so, example of an odd cycle right here. This is a cycle on 1, 2, 3 vertices. So it's a 3 cycle. N cycle is the number of vertices on your cycle, and that at 3 is clearly odd. And so that means that this graph on the right is definitely not bipartite. There is no way to partition. And the proof of that we covered before. The problem is and it was a homework problem, the problem is that when you have an odd cycle, if you enumerate and say, let this be an A, let this be an B, and let this be an A, eventually you get an edge that's between two members of the same group, and that's forbidden. On the other hand, this graph on the left, if you look at the cycles, there's 1 6 cycle, There's a 4 cycle here, there's a 4 cycle here, a 4 cycle here, and at least one other 4 cycle I'm not seeing right now. We don't see any odd cycles. So according to the theorem, this should be bipartite. So of course the question is, how do you determine if it's bipartite? Well, you just start doing the following algorithm. You pick your favorite vertex, you color it blue. Blue's going to be my set B, and my set A is going to be red. And then what you do is, for every blue vertex, you look at its neighbors. These are his 2 neighbors. They're the vertices that share an edge with blue, and you color those vertices red. I've done this for all blue vertices, so now I switch colors. And now I look at the red vertices. Every neighbor of a red vertex that hasn't been colored yet, I color blue. So there's an edge here, so I color it blue. There's an edge here, and there's a red vertex, and that one's uncolored, so I color it blue. And I've exhausted all neighbors of all red vertices, and so now I switch colors again, and now I look at all blue vertices, and I look for edges incident to a blue vertex where the other endpoint's not colored. I see this vertex, and so I color it red. And you keep doing this until you've colored every vertex, and that gives you bipartition. And so to emphasize that, I've chosen to redraw it. I've labeled the vertices 1 through 6, and now I've redrawn the blue vertices together, 1, 3, and 5, and the red vertices together, 2, 4, and 6, and I've drawn the edge connections. So these 2 graphs are actually the exact same graph. This is just a different drawing of it, and in this drawing you can clearly see the bipartition. So as another example, let's look at this graph. Please note that this vertex is connected to this one by an edge, but to make it clear, I've drawn it underneath the other one, so it's like there's an overpass here. Is this graph bipartite? Well, it doesn't look like there's any odd cycles, so we think it might be. So let's try using our coloring algorithm again. Pick any vertex. I'll just pick this one at random. Now color its neighbors red. We've colored all of its neighbors. Now go to the red vertices and color their neighbors blue. Now we've colored all their neighbors, so we switch back to red, color all the blue vertices, neighbors red. So here's one blue vertex. Let's color its neighbors red. There's a neighbor. There's a neighbor. We've used all its neighbors. Go to the other blue vertex. There's its 2 neighbors. And if you notice, once we switch colors again to blue, we see we've got a problem. Here's an edge connecting 2 red vertices. And that tells us that we should be able to find an odd cycle in this graph because it's not bipartite. And let's see if we can find it. The easiest way is to just take a closed walk. So I'll use the color green, using only colored vertices we've already colored. So how about that one? 1, 2, 3, 4, 5. And there we go. We found an odd cycle in the graph. Therefore, this graph is not bipartite. And so sometimes it's easy to find the odd cycle, and then you just list the vertices. So if I gave these vertices names, and my boss were to ask me if this graph forms the network of a 2-party system, I'd say, well, no, it doesn't, because representatives 3, 4, 8, 9, and 11 can't be partitioned into 2 groups, because there's an odd cycle there. And so this graph can't be bipartite. If this didn't happen, then I would have been able to finish my algorithm and colored everything like I did on the previous slide, and then I'd have a bipartition. And so that's really all I have to say about bipartite graphs for now. To check if a graph is bipartite, you use this double coloring algorithm, and if you ever get 2 colors connected by an edge that are the same color, then you have a odd cycle. And so find the odd cycle. And so either you find an odd cycle or you find a bipartition.